in this problem, we're going to be looking for the amount of a product. So that's a stoichiometry problem. But we also see that it's a gas laws problem because we have a gas collected. So let's look at what we have given. Of course, we have a volume here. Then we have this part about it collected over water. So anytime you have a gas collected over water, which our gas in this case is oxygen, but if it's collected over water, that means that it's going to be mixed with gaseous water. So that brings up Dalton's law of partial pressures. The total pressure, or the pressure of the mixture, is going to be the sum of the partial pressure of water and the partial pressure of the other gas that you're collecting. Okay, and we have a temperature and a pressure. We're looking for moles of pure oxygen, so we're looking for this. And we have a vapor pressure of water. Here's another temperature, but you notice it's the same one. 25C is 298 K. And we have another pressure. Okay, let's make sense out of our two pressures. What is what? Well, this one that says vapor pressure of water, that is going to be our partial pressure of water. The one that says the gas is collected is going to be our total pressure. It's the total pressure of the mixture. So one other thing we might think about is anytime you have a gas mixture, you may use this kind of specialized version of PV equals nRT, or ideal gas law, where you have it specific for one component. And since we are solving for, we want moles of oxygen, I'm going to put O2 there. And the only other thing that changes with that is I need to make sure that the pressure I use is the partial pressure of oxygen only. Okay, so let's see what we have. We have our total pressure is given. This is given. So we could get the partial pressure of oxygen. If we do that, then we could put that in here. We have the volume, we have the temperature, and yes, we could get our moles of oxygen. So that's our plan. We'll use this one, then this one. Notice that both the pressures have to be in the same units in order for you to subtract. The volume is the same for both gases in the mixture. They occupy the same space. Okay, and so that gives us our moles of oxygen. Okay, and so let's look at our part B. Part B asked for the percent yield. And as you know, percent yield is going to be actual yield over theoretical yield times 100%. Well, this is a yield that we just found. This is a yield. Is it actual or theoretical? This one is an actual yield. And the way that I know it's an actual yield is that it is what it was observed. We collected an amount of gas, and this is how much oxygen must have been in that. The other way of knowing is that I did not use stoichiometry to get it. Theoretical yields rely on you using the coefficients and stoichiometry to make a prediction based on the amounts of the reactants. I didn't do that. I just looked at the volume collected and used gas laws to say how many moles of oxygen were in there. So that is our actual yield. We need a theoretical yield. So let's calculate a theoretical yield. So to get our theoretical yield, I'm going to look at the amount of my reactant. Stoichiometry is conversion factor problem, and this is, we have to label what's what so we don't get them mixed up. We don't want moles of potassium chlorate. We're interested in moles of oxygen so we can compare to this actual yield. To get the numbers that go in here, I'm going to use my coefficients from my equation that are highlighted in yellow there. This is the stoichiometry part, which will give us a theoretical yield. Now I'm not going on to grams because I need the amount of oxygen in moles to match this actual yield. They have to be in the same unit. Okay, and this is our theoretical yield. And then for our percent yield, it's actual over theoretical times 100. So and there we have it.